Hi there. In this video, we're going to start Chapter 6. We have 4 more sections to go, so let's get started. So I just want to do a quick introduction of Chapter 6. When most people think of statistics, this is probably what they think of as the stuff we're going to do in Chapter 6, where we have lots of formulas. At the end of the video, I'll show you the formula sheet that we're going to be using. So on that test, you'll be provided the formula sheet. Obviously, you still want to learn how to use the formulas on your own. Don't count on being able to just look at this big formula sheet and pick out the right formula. You still have to learn how to use it, right? So what are we doing different in Chapter 6? Well, there's 3 main new things that we're going to do, but there's very little that's theoretical. This is mostly practical new things that we're learning. First one, it's not always convenient to use stat keys, so we focus on using only the graphing calculator to solve problems. So that's our main objective, is how do we get away from stat key? We will use formulas to compute the standard error of distributions of sample statistics. So that's the main difference. Up to this point, you had to be given the standard error, or you had to go into stat key, make a bootstrap distribution, make a randomization distribution, and get the standard error. We're going to use formulas, and that's actually the main topic, is using these formulas. Number 2, we introduce a new bell-shaped distribution called a t-distribution. So that's going to be in section 6.2, so it's a few videos away still, because the section order is out of sequence intentionally. So this will be like halfway through Chapter 6 where we'll introduce this t-distribution. And the last thing is actually quite easy. We determine how large a sample needs to be so that the distribution of sample statistics can be replaced with a normal distribution or a t-distribution after we learn it. So up to this point, in Chapter 5, we learned about the central limit theorem that says if a sample is large enough and random, we can replace the distribution of sample statistics with a normal distribution. But we didn't know exactly what that meant. So we're going to learn exactly what that means here in Chapter 6. So because we're building on previous knowledge, I just made a list of probably the most important things that you have to be able to do before we do the new stuff from Chapter 6, right? All of this stuff is always in effect. Samples and populations, that was from Chapter 1. Categorical quantitative, explanatory response, all of that is from Chapter 1. And then we learned the sample statistics and names of the parameters in Chapter 2. We didn't call them parameters in Chapter 2. We didn't learn that name until Chapter 3, but we learned what p hat and p were and things like that in Chapter 2. Then we need to be able to find the center of each of the different distributions, our sampling, bootstrap, and randomization distributions. We're going to be doing all 3 in Chapter 6. So you have to know where these things are centered when you build your distribution. You need to be able to find your null parameter value for a given set of hypotheses. You need to be able to find your critical value z star for a confidence interval using your inverse norm. You need to be able to find a confidence interval given a z star value and a standard error. So that bullet and the previous one came from Chapter 5. You need to be able to find a standardized test statistic z for a hypothesis test, which also came from Chapter 5. And of course, the last one is a combination of things from Chapters 4 and 5, right? If I give you a set of hypotheses or you come up with your own, you need to determine the tail of the distribution and find a p-value. So I'm not going over how to do any of this stuff. This is all stuff from previous sections. If I'm going through the examples in Chapter 6 and you don't recognize one of these things, go back and find it. If you're not sure where to find everything, look at the exam review material. There's a checklist. The checklist explains where everything's located in each section, and you can use that to reference the notes or the book section if you need to look something up. Because the PowerPoints aren't great for looking stuff up, right? They're not designed as a reference tool. So here are two reference tables. If you do need them, these are in the beginning of the section here. The first one is the notation for parameters and statistics. These are the only ones we're going to use, right? And these are the ones we used mostly in chapter 5. In chapters 3 and 4, we did some correlation stuff. Really don't do much correlation in chapter 5, and we don't do any at all in chapter 6. So there's your notation. Make sure you know your notation. And then at the bottom, the center for the distributions. Also make sure you know that. So just a little bit of reference material if you need to go back and look this stuff up. So let's start section 6.1. So the way this is broken down is now we're going to look at, well, let me back up a little bit. Chapter 3 was confidence intervals. And when we did confidence intervals, we mixed up all the different statistics and parameters, and you had to identify which one you were supposed to use when you did a confidence interval. Here we're flipping it around and we're saying we know the variable, we know that it's going to be a single proportion. So we're going to look at hypothesis tests and confidence intervals, and that's what's going to kind of jump around, is the type of analysis needed. But the variable and the parameter is set, right? So I'll let you read the section learning goals. So here we go. So there is some reference material here, but I'm just getting it set up so we can start working with the new stuff. So for one categorical variable, the parameter of interest is, of course, the population proportion P. In section 5.1, we saw the central limit theorem that said the sample statistics follow a normal distribution if the sample is large enough, and it has to be randomly samples as well. But the main thing here is that it's large. We always need random sampling, right? Bullet 3, the distribution of sample proportions P hat follows the distribution NPSE. Let's talk about this real quick. So what this is saying is that, at least at this stage, right, the distribution of a proportion, we're saying that assuming we have a large sample, the distribution will be normal. Okay, that makes sense. So it's normal. It's centered at the population proportion. Whether we know the population proportion or not, sampling from a population, the center of all of the samples we take will be the true population proportion. And of course, the standard error is the variability. So if we have a normal distribution, it's completely determined by the center and standard deviation. When we're doing sample statistics, of course, we call the standard deviation a standard error. So in chapter 3, we saw how to use a bootstrap distribution to do this. And in chapter 4, we saw how to use a randomization distribution. In this chapter, we're going to use formulas. So let me show you the formulas. So we're not going to do as much stat key in chapter 6. You can always check your answers using stat key, though, because it is easier to use than the graphing calculator. But on a test, I want you to use the graphing calculator because I want you to show the steps. I want you to show the work. So here are the two formulas for this section that we need, at least early on. There's more formulas coming, of course. So if our sample size n is large, then the distribution of sample proportions from a population with known proportion p has that distribution. Okay, so the idea here is we're saying that we know p. Even if we don't, repeated sampling is still centered at the population proportion, right? But the idea here is that we're not doing repeated sampling. We're going to be taking one sample, or we're going to be reading about studies that take one sample, and then we want to know about that sample. So the first thing we're going to look at is the large samples condition. So what does it mean for a sample to be large? Well, it turns out that the samples don't have to be very large at all. In fact, you just take the sample size times the known population proportion. Again, we're assuming it's known for this calculation. You just do n times p and get 10. And if you get a number bigger than 10, great. Or if you get 10, great. That's a large sample. Also, we need to do n times 1 minus p that also has to be 10 or larger. So we just have to check those two numbers. If the sample is large, so if it satisfies both of these conditions, then this is true. We already know P, right? It's given in this setup that we're going to know P. And how do we figure out the standard error? Well, here's the formula we're going to use. So this is like the basic design that we're going to use moving forward in this section and the next one. Now, if it turns out we don't know P, so let's say we're doing a confidence interval, we just put P hat in for all of these formulas. So the formulas don't change much. We just replace P with P hat. Again, you will have a formula sheet that has all this stuff on it. And then if we're doing hypothesis tests, we replace P with P0 with the null parameter. All right, let's see how to use these formulas. So verify that each of the samples below are large enough for the central limit theorem to apply. Use the formula to compute the standard error. So we have two things here, right? So we're just going to use both of these formulas, well, all three. So we're going to check that the samples are large first, and then we're going to compute the standard error if the samples are large, okay? So the first one we're going to do is n times p, right? So that's just 50 times 0.25. And you get 12.5. Well, 12.5 is bigger than 10, so we're halfway done. Then you do n times 1 minus p, right here. So 50 times 1 minus 0.25, just like that. Also bigger than 10. So because both of these numbers are bigger than 10, our sample is large enough to use this formula. So let's do it. All right, next we're going to compute the standard error. If you have a TI-84, I recommend that you go ahead and just build this thing the way it looks, right, using the formula. So you can see what this looks like, right? So what you want to do is you want to find like a big, just take a square root. Oop, wrong button, sorry. Where'd it go? Oh, here it is. Build a square root. Then just put a fraction on the inside it. So I'm kind of building a stacked fraction here. It's really the easiest way to do it. So look at what it says. P times 1 minus P over N. Oh, I have all those, right? So it's going to be 0.25. Oop. 0.25 times. You don't have to type times. Just parentheses. It does multiplication on these calculators. 1 minus 0.25. And N is 50. So that's all you have to do, right? Just type it in exactly the way it looks. You'll get a kind of a weird decimal, but that's okay. That's the number we're looking for, and then we'll round it to some amount or another, right? So there, you can see that it's 0.0612. So I rounded it to 4 decimal places. Just on the homework, follow the directions. If this is on a test, just follow the directions for rounding. So you can see these are both bigger than 10. I went ahead and did this on the calculator. And then the standard error. So if you had to use this to figure something out, the distribution of all of the sample statistics of size 50 from a population where P is 0.25 is centered at 0.25 with this number representing the variability, right? So if you had to do a 95% rule or something like that. All right, let's look at the second one. So we're really just going to do the same thing. So it's it's n times p for part B, n times p. It's 10. 10 is greater than or equal to 10. And 100, oop, don't need the times 1 minus 0.1. Right, so both of these are larger than 10. So we can use the standard error formula. So build a radical, put your fraction in there, and just type it in the way it looks. 0.1 times 1 minus 0.1 over 100. right? And it works out pretty nice. I went ahead and tacked on the 2 extra decimal places just for 4, just to show you that I'm not rounding it to 2, right? It's 0.030, like, it's actually 0.03. I just didn't want you to think I rounded. Okay, so, oh, sorry, let me leave this up. Let's look over here real quick. So what I really want you to notice here is that NP and N times 1 minus P, so P and 1 minus P are complements, right? These add together to make 1. And when you multiply by N, that means this number plus this number will be N. So you don't have to use the formula if you don't want to, right? If you know that 100 times 0.1 is 10, then you know that the remaining items that we're trying to count adds up to 100. So 10 plus 90 is 100. So you actually don't have to show work on these sorts of calculations because you're going to be using your calculator to do the vast majority of this. Really, all you have to do is just identify the value. So I'll ask you, what's the sample size? What are we trying to satisfy? What condition are we trying to satisfy? And you're really just typing everything into the calculator. So in some of the future steps in this video, I'm going to show some intermediate steps, but you really don't have to. As soon as you have something like this, you can just write the answer down because your calculator's doing it for you. Not everybody has a TI-84. If you have a different calculator, then some of the examples later in these notes, I do include the intermediate steps. You really don't have to. Just show me what you're typing in, and then you can just write the answer down. That's totally fine. Alrighty, let's keep going. So in order to use the standard error formulas, the sample must be large enough so that NP is greater than or equal to 10, and N1 minus P is greater than or equal to 10. This statement is often expressed as the sample has at least 10 successes and at least 10 failures. This terminology is in reference to the formula for a proportion, P hat equals X over N, where X is the number of successes in a sample of size N. So we introduced this formula way back in chapter 2, but we didn't use this terminology of successes and failures. The reason I'm introducing it now is it's actually much easier to express this concept using a little bit more plain language, right? So the idea here is that if we're counting how many things in our sample satisfy this condition that we're looking for, it's a lot easier just to call those successes. It doesn't have to mean anything like success means in the real world. So if you're counting what proportion of people get heart attacks in a sample, then your successes are the people who have heart attacks, or the proportion, and then you measure the proportion of people who have heart attacks. Those are your successes. Whereas you don't really think of heart attacks as being successes in the real world. That's not what it means, right? This is more of a specialized mathematical thing where whatever we're looking for, whatever we're counting, those are the successes. So any observation that is not a success is called a failure. And it's just going to make this a lot easier to talk about because you don't want to listen to me say NP greater than or equal to 10, N times 1 minus P greater than or equal to 10. Right? Spoken language and mathematical symbols don't really mix, so we just call them successes and failures. If the sample does not satisfy the large sample condition, we cannot use the standard error formulas from chapters 5 and 6 based on the normal distribution. In this case, we would need to use the bootstrapping and randomization techniques from chapters 3 and 4 because they have no explicit minimum sample size restrictions. So if you recall, we saw what a bad bootstrap distribution looks like, right? The only requirements for a bootstrap or randomization distribution is that the distribution is symmetric. It doesn't need to be bell-shaped, right? When we're using these standard error formulas, we do require that we have a bell-shaped distribution. And so small samples might cause the distribution to not be bell-shaped. So if you're using these techniques in the real world, if you were taking a class where you had to analyze, let's say, a small sample, and the sample size was too small to use the standard error formulas, you could always go back and do a bootstrap distribution or randomization distribution. If the distribution looks okay, then it's fine. Your answers will be fine. Remember, a lot of that's based on what it looks like, right? Is the sample size large enough so that the sample proportion follows a normal distribution? Well, we're just going to do the same thing, right? N times P. So it's 92. That's bigger than 10, so that's fine. But what if we do N times 1 minus P? Well, that gives us 8. 8 is not bigger than 10. As soon as this happens, we need to stop using the formulas. So if you were trying to use this, let's say you were analyzing some data and you had these numbers, you'd have to stop and go back and try what you're trying to do in a bootstrap distribution or randomization distribution. We wouldn't be able to use these formulas. So make sure you can do both. So here is some pictures that justify these large sample conditions. So in each of these graphs below, the sample size is 50. So this is just a mix of different P's, right? So these are all different population proportions. So look at what happens if you take a sample of size 50. This is the distribution of sample statistics if P is 0.05. Does this look symmetric and bell-shaped? It doesn't. Right? What about this one? Does this look symmetric and bell-shaped? No, not really. Skewed right. Both of these are skewed right. What about this one? Does that look symmetric and bell-shaped? Sure does. Symmetric and bell-shaped? Yep. Symmetric and bell-shaped? No. And this one's just really strange looking. So the only graphs we're seeing here that are symmetric and bell-shaped are C and D here, right? Well, what makes these special? And what makes the other ones not what we want? What is it about these that what characteristics do these two graphs have? Well, it turns out that if you do N times P and N times 1 minus P for all of these graphs, the only two graphs where NP is greater than 10 and N times 1 minus P is greater than 10 is this one and this one. Right? We actually did this one as one of our examples, right? This was the 50 times 0.25, right? It was this one right here, right? 50 times 0.25. Right? It was the first one we did. So the first one we did is actually this graph. So when this large sample conditions are satisfied, we get a nice symmetric bell-shaped distribution. It turns out we can replace that with a normal distribution. All these that are skewed, something is wrong. So let's look at this one. This one's not really skewed, but it's too skewed for us to use the formulas. Because N is 50, P is 10, N times P, so 50 times 0.10 is 5. 5 is not bigger than 10, so we get a skewed distribution. So that's how it works. So it turns out that those formulas don't come from some sort of deep mathematical principle at all. What happens is that a bunch of mathematicians and researchers made a bunch of graphs and looked at the ones that appeared to satisfy this normally distributed condition. And then they looked back and said, well, what is special about the ones that appear normally distributed? And that they came to an agreement. Now, this is not universally held agreement. Different fields of study have different large sample conditions, but we're picking sort of like the most commonly used one. That the researchers who came up with this, they said, well, we want to have a nice symmetric bell-shaped distribution of sample statistics. So they set the criteria for that at successes equal to 10, failures equal to 10. And it works pretty well, as it turns out. Let's do some confidence intervals. So in section 5.2, we saw that when a distribution for a sample statistic is normally distributed, a confidence interval can be formed using sample statistic plus or minus z star times the standard error, right? We did a bunch of work with that in section 5.2. So here are the formulas that we use. Notice when we're doing confidence intervals, this looks really similar to our large sample condition that we just finished doing, except when you do confidence intervals, you don't know the population proportion, so you can't put p in the formula. Instead, you use an estimate for p. The best estimate we have for p is, of course, p hat, so we use p hat in all of the formulas. And that's how it works. So we're going to be checking np hat greater than or equal to 10 and 1 minus p hat greater than or equal to 10. This is still successes and failures, because that successes and failures come from the individual samples. Notice the standard error formula, very similar to the one we just saw, except instead of p, we use p hat, of course. Now, we're doing a confidence interval, so we need to understand the margin of error. The margin of error is everything to the right of the plus minus in a confidence interval. So all of this over here is our margin of error. And we know the formula for confidence interval, right? I just took it from here. Sample statistic is going to be p hat. Standard error is given by the formula. And z star, we know how to find z star. So we know how to do all this stuff. Right? P hat plus or minus z star times the standard error. And again, everything to the right of the plus minus is what we call the margin of error. This has not changed since chapter 3. None of this is new, right? The only thing new so far in this chapter 6, the large sample conditions and the standard error. And we just saw how to compute that in the previous few examples. So let's jump in and do one of these. Use the normal distribution to find a 95% confidence interval for p, given that p hat is 0.38 and n is 500. So we want the best point estimate for p, the margin of error, and the confidence interval. All right, so what is the best estimate for p? This question, one just like this, was on the test and a bunch of people missed it. It was on test 2. A bunch of people missed it. Don't miss this stuff, guys. You got to know how to do estimates. So either best estimate, point estimate, or best point estimate, they all mean the same thing. Our best point estimate is, of course, p hat. So we're trying to find p. We don't know p, but we have a good guess where it is. That good guess is called p hat. All right. What about the margin of error? Well, if you go back one slide, the margin of error is z star times the standard error. So the way I'm going to do it, I'm going to compute the standard error first. We already know z star, right? Z star, you should have memorized it in chapter 5 for a 95% confidence interval. If you didn't, pause this video and get your chapter 5 notes out and look up z star for a 95% confidence interval. You're going to need it. All right, so let's do, right, so there's your standard error, right? 1.96. Sample size is 500. So use the standard error formula, right? So this is just the same thing we did in the previous example, right? It's just p hat times 1 minus p hat over 500. So go ahead, type this into your calculator now. Make sure you can get this answer. So pause the video and make sure you can get this answer. I'm going to move on, but I want you to try it. Next up, the margin of error is just z star times our standard error. Z star is 1.96. Standard error was computed in the previous part of the problem. After you multiply it, you don't need to keep 4 decimal digits. You're allowed to keep extra decimals if you want, but for a problem like this, you don't need to. So that's the margin of error. That's the standard error. And for part C, we need the confidence interval. So we're just going to use the formula. Notice we've already computed all of this stuff. The sample statistic is here. It's p hat. Z star times the standard error is here. It's 0.043. Just plug in everything. We already have all these numbers. And of course, that's your answer. So pause the video. Make sure you can get these numbers. Double check everything. On the homework, follow the directions for rounding. I'm just keeping 3 decimal places for my final answer here, but it could be different on the homework. The homework jumps around a little bit with rounding. Alrighty, well, that's pretty much all you have to do. For problems like this in Chapter 6, you'll have the formulas in front of you. Again, you have the formula sheet. I'm going to show you at the end of this video, I'll show you in Canvas where all this stuff is located. Right? So if you want to stick around at the end of the video and look at a little more technology, that's totally fine. But I'm just going over basically what you got to know for tests. All right, now we're going to look at determining sample size. A common question when designing a study is, how large a sample should we collect? The answer to this question depends on 3 related questions. What margin of error do we want? How much confidence do we want to have in the interval? And what sort of proportion do we expect to see? So we saw problems like this at the end of Chapter 4 in the notes and in the video. We saw that if samples are too large, that the study could get statistical significance without practical significance. So if you are a researcher, you don't want samples to be too big. So what you really want to do is figure out the margin of error. So that's sort of the range of acceptable practical results. You determine the confidence, how sure you want to be. So if you're testing a heart medication, you probably want to be really, really sure. If you're trying to set your fantasy football lineup, you don't need to be as sure. And what sort of proportion do we expect to see? So just where do we think the center of the distribution is? So those are all things that the researcher wants to specify. And there's a formula that will tell us the best sample size to collect to get those results. And here's the formula. Yes, it is ugly, but you just got to deal with it. So it's this guy here, right? N equals Z star over margin of error squared. So that whole thing squared. And then this symbol is called P tilde, and it's P tilde times quantity 1 minus P tilde. So this is another estimate for P, right? We would like to use P hat. Why can't we use P hat? So I'll let you think about that. I'm not going to give that answer up, but you should be able to figure out by the end of the video why we can't use P hat here. So we use P tilde equals 0.5, or if available, some other estimate of P. So the reason we use 0.5 is 0.5 is sort of the maximum amount of variability. So if we use P tilde is 0.5, the distribution will have the widest spread. And because we're trying to get our answer within a certain margin of error, this is called like a conservative estimate. Like we want to be really, really sure. So this is the number to use. Or some other estimate of P. You might be given in the problem some other estimate to use. What sample size is needed to give a margin of error within plus or minus 11 percentage points in estimating a population proportion with 99% confidence? So I'm just going to take all of this stuff and plug it into this formula, right? So it's a 99% confidence interval. What's Z star for 99%? If you didn't say it out loud, you need to go look this stuff up. It's 2.576. Margin of error, right? So if the margin of error is plus or minus 11%, what number are we going to type in here? 0.11. It doesn't matter if it's plus or minus, because we're about to square it, right? Negative numbers squared are still positive, so you just type in the positive number. And what p tilde should we use? Well, we're not given a p tilde, so we have to use 0.5. Right? Put everything in the formula like that and crunch it. So type that in exactly the way it looks, right? So again, if you're not sure how to do this, that's weird. Hold on. My calculator's not working correctly. There we go. That was really strange. So what you might want to do is do some parentheses, put your, like put your fraction in parentheses so you can put a squared on the outside. So 2.576, 0.11 squared, and then times 0.5 times 1 minus 0.5. And just crunch it up. So you may have noticed that I did something that you never, ever, ever do in math. This is the time you do it. You round this answer up to the nearest whole number, no matter what. This number is not allowed to be a fraction, and you're not allowed to round down. Okay? Whenever you do these sample size calculations, you have to make sure that we satisfy the margin of error calculation. If n is too small, so if we round down, this margin of error might not be satisfied. So we just always round up to be safe. So if you did it correctly, you should get the right number. Just type it in just the way it looks, and you'll get the answer. All right, last topic is hypothesis testing. So in section 5.1, we see that when a distribution of a statistic under the null hypothesis is normal, we compute a p-value using n01 and a standardized test statistic z. So this is what we used in section 5.1. There were other methods given in section 5.1, so if you haven't practiced this method, you're going to have to know it to do this. But we'll practice it a little bit. There's your large sample conditions. Notice here that P has been replaced with P0, which is our null value, null parameter value. The standard error, P, has been replaced with P0, obviously. And our standardized test statistic, this is actually the same thing we used in Chapter 5. This is new for Chapter 6. This is new for Chapter 6. This is the same formula from Chapter 5. And then we're going to use the alternative hypothesis, the z value, and the normal CDF to find the p-value. I went ahead and put the instructions in here again. It's the same stuff from Chapter 5, but as a reference, I went ahead and put it in here. I'm not going over it again. If you forgot how to do this, just go back and do Chapter 5 again. This is just for reference. So let's do example 5. Use the standard normal distribution and the given sample results to complete the test of the given hypotheses. Assume the results come from a random sample and use a 5% significance level. All right, so test p equals 0.6 versus p greater than 0.6 using the sample results with p hat at 0.74 and n equals 76. So you do need to check that the sample is large, because that's something I can ask you on a test, right? I can combine questions together. So even if you're not asked to do it separately, you should check that the sample is large, right? So here's everything we have. And to check that I didn't put in the notes, I'm just saying it's something you got to be able to do, right? So 76, so n times p hat, which is 0.74, and n times 1 minus p hat. All right, make sure those are both greater than 10. So it says complete the test of the hypotheses. So we're just going to go through. We're just going to go through all these things here. So I checked that the sample was large. Even if you're not asked to do it on the homework, make sure you can do it. Let's do the standard error, and then we're going to do the standardized test statistic. All right, so the standard error, just plug everything in the formula, right? So remember, we use P0 here, right? So 0.6, 1 minus 0.6 over 76. So I know you can do that calculation, right? Just type it in. If you're not sure, pause the video. Go ahead and do it on your calculator. Make sure you're getting this number. Then for the z, it's p hat minus p0 divided by the number we just computed, which is the standard error. And you should get 2.49. Now we're not done, right? We just found the standardized test statistic. What you need to do now is draw the picture of the distribution, label z, shade the appropriate tail, and then use normal CDF. So let's go through it together. Before we go to the next slide, we'll just say everything out loud. So is this a two-tail or, sorry, is it a left tail, two-tail, or right tail? This is right tail. And so 2.49 is going to be way on the right side of the distribution, and we're going to shade to the right. So it looks like that. So now we just use the techniques from chapter 5, normal CDF. The left endpoint is 2.49. The right endpoint is just some number way down on the right side. So I use 10,000. You can use any big number that you want. 0 and 1, but those are the default settings. And you get a p-value of 0.006. Right, so that's our p-value, 0.006. And because our p-value was smaller than alpha, 0.05, we reject the null hypothesis and accept the alternative. So if we knew something more about the context, we could say more about the context. This is just a theoretical constructed problem. So there's nothing more to say here. And that's how you do it. So once you get the standard error computed, these turn into problems that look like the ones from chapter 5. Make sure you can draw these. You must be able to draw these things. Those will be on the test. And make sure you can use your normal CDF. So a two-tail, you do the same thing. You would just double it on a two-tail, right? All right, let's do another one. So use the standard normal distribution. Oh, I already read all that. So this is just a different setup, right? P is 0.25 versus not equal to 0.25. Our sample results are 0.21, N is 44. Same sort of thing, right? So our null value is 0.25, P hat is 0.21, N is 44. And this is a two-tail alternative hypothesis, right? It's a not equal. Compute the standard error. Again, go ahead and pause the video and check that you can get the same number. Test statistic. And then, draw your graph. Negative 0.61 is going to be on the left side of the graph, but fairly close to the center, and you're going to shade to the outside. And then you're going to double it because it's a two-tailed alternative hypothesis, right? So, your left tail is way, way down on the left. Your left endpoint is way, way down on the left. Your right endpoint is negative 0.61. 0.1, you should get 0.271. And if you use StatKey to check your answer, you'll see what it looks like. You should be drawing these by hand, though. We're going to double this because it's a two-tailed test. This is a very large p-value, so we do not reject the null hypothesis. So this should look familiar as the stuff you did last week, right? In chapter 5. The only things we're doing are checking large samples and computing the standard error. That's it for the new stuff. So we're not tacking on that much more information, right? I went over at the beginning of the video that there's really only 3 new things in chapter 6. And you can see that we're using 2 of them. And in a couple more sections, we'll use 1 more. Many of the problems in chapter 6 look like examples 3, 5, and 6 from the PowerPoints in this section. During the remainder of the course, you will see several ways to solve problems like these, and you will need to select the solution method that personally works best for you. So I've talked about that a little bit, right? How much work you want to show. I want you to draw the pictures for every problem, but I can't make you do it. If you can get these problems right without drawing the pictures, then you're probably going to be fine. But if you're getting the answers wrong and you're not drawing the pictures, then draw them. The methods used in the PowerPoints are the most general methods, and they work in every situation. So I'm going over stuff that I might not even need to go over. Other optional shortcut methods outlined in some Chapter 6 handouts and videos don't cover all the details for every problem, but they do give the same answers for confidence intervals and p-values. So that's what I'm going to talk about next. If you don't want to know the shortcut methods, and they're not super duper shortcut, they're going to save you about a minute per problem. If that seems worth it, then stick around. If you are dedicated to just using only one method and that method always works, then you don't have to watch the video after. I'll make an announcement in about 2 minutes that I'm going to move to the technology stuff. Every confidence interval in Chapter 6 has the same general formula. So we saw both of these when we did our confidence interval example. To solve problems like these in Chapter 6, find the sample statistic first. We did that. Find the standard error and the z-star value. Combine these if necessary to find the margin of error. We did that. Compute the confidence interval and interpret it in context if necessary. So steps 1, 2, and 3 are very general. Sometimes that's more work than you need to do, but sometimes it's better to do more work because the homework and the tests can ask the problems in lots of different ways. Every test statistic in Chapter 6 has the same general formula. To solve problems like these, find the sample statistic first. So that's the same no matter what, sample statistic first. Find the standard error. It's always the second step. And the null parameter value. Compute the test statistic. Part 3, use the test statistic, the alternative hypothesis, and the normal CDF function. Or when we see the t-distribution, you'll use the t-distribution to find the p-value. So these are the most general methods. They always work. They're not fast. You can see how long it's taking to do a few problems, right? It takes a long time. So that's it for the main stuff. If you want to stick around and look at some shortcut methods, I'm going to show you those right now. Alrighty. All right. This shouldn't take more than 5 minutes. We're at 48 minutes right now. Oh, wrong one. There we go. All right. So if you want to just watch this or you want to follow along, that's fine. So I went to the Canvas course. We're in week 12. Oh, sorry, week 13. Sorry. We're in week 13. And you can see that there's a lot of stuff here in week 13, right? You got to do your adaptive practice from chapter 5. Now, there's something called these 2 video tutorials, and of course, these additional worked out examples. So what I'm going to show you, I'm going to go ahead and show you how to do one of these I'm going to click on this. Then I'm going to show you what the shortcut methods look like. We're not going to watch the videos inside this video. You can watch these videos on your own. I didn't make these videos. You're allowed to use these methods if you take the time to learn when you can use them and when you can't. You're allowed to use them. And I'll show you a situation where you might want to use it. So let me click on these additional worked examples, and I'm just going to download it. Just to show you. All right. So these were made by Katie Dobeck, who does a great job as the coordinator for the course. Here we go. And I know it's hard to read, but that's okay. What this is a good way to test showing all your work, right? So what I'm going to do, I'm just going to do this first problem sort of live on the calculator just to show you how this worksheet works and how to use the shortcut methods. So look at the way this is broken down. Point estimate first. That's your sample statistic. Margin of error second. Right? Margin of error is your standard error and your Z star. This is a confidence interval. And then, write your confidence interval. And then check, NP is greater than 10, N1 minus P is greater than 10, right? These got to be hats, though, for confidence interval. And this is what we did sort of in class, right, so far. Right? Draw the picture. Use the formulas, right? So this is what I just got finished doing earlier in this video. Not for this problem, a different problem, but basically the same. Over here, we have this thing that says solution 2. So for these handouts, solution 2 in chapter 6 will be this shortcut method. So let me show you how to use the shortcut method. You're allowed to use it. You're allowed to use it on tests. All right, so the way this works, let me go ahead and clear this whole thing. Oh, that's weird. Huh, this thing's acting really strange. Try this again. All right, that was really strange. Okay. So you go stat, tests, 1 prop Z interval. So we're going to do a 1 proportion Z, that's your test statistic, interval. So we go stat, tests, over here. And then down here, you'll see it. It's way down here. It's like, there it is. 1 proportion Z interval. Now, you have to type it in the right way. Okay, so X, that's the number of successes, right? So when you check that your sample is large, right, the number of successes is N times P hat. So for this problem, for this given problem, right, N is 525, P hat is 0.4. So, you would have checked ahead of time that the sample was large. And you can see it's done here in the problem. We already practiced that, so I'm not going to go over it. And what you do is you just type in whatever number that would be. So we see 525 times 0.4 is going to be 210. So, but you can see that you can type formulas into here and it'll compute it for you. Right? See what it says here? 0.4 times 525 is 210. N, then you type in N. N is 525. Confidence level, that will always be given in the problem, right? A 90% confidence interval, right? So 0.9, and that's it. Oop, I messed it up. Let me try it again. This app works a little different than the handheld. Oh, there it is, there it is. It comes out at the top. 0.36483, 0.53517. So if you're rounding to 3 decimal places, 0.365, 0.535. Now, what if you have to work backwards and find the margin of error? Well, remember, the formula for a confidence interval is sample statistic plus or minus the margin of error. So that means you can take one of these endpoints and subtract the sample statistics. So you can do 0.435 minus the sample statistic is 0.4, right? That's given in the problem. So the margin of error is 0.035, right? Which is what you can see as the correct answer up here. So that's how you use these shortcut methods. If you want to use them, once you get the hang of them, they are indeed faster. You'll save about a minute per problem on problems that look like this. If you don't want to use them, then just forget the last 8 minutes that you just saw. However, regardless of which method you use, you still should check out these examples. They're really cool. And there's a bunch of problems. There's usually like one confidence interval and one hypothesis test. Each one is done using the formula method and the shortcut method. You are not required to use the shortcut methods in the class, but you do have to be able to use one of the two methods to get an answer on a test. As long as you tell me which method you're using, you'll be fine. Well, that's it for this video. I'll see you again real soon for the next video when we continue Chapter 6. All right, that's it for today, and I'll see you next video. Bye-bye now.